because you just tell me 0 or 1. Maybe you just flip a coin and decide every time. After you decide the upper triangular part or any triangular part, then the other part is implied by the symmetry. No one is going to
Write all non-diagonal elements 1.
Pardon? All elements 1 except the main diagonal.
Yeah.
Yes.
That's 0.
You get complete graph of all the 10. So complete graph comes out again as a TFS graph, right? Because every vertex is adjacent to every other vertex. Now let us, nobody volunteers to shout. I like people shouting in the class, but I don't think some people think that you are being rude, but I don't mind because nobody wants to shout. Then I have to shout. Maybe this is published from a published paper of mine. So let me have a 7 by 7 Theoretic matrix, symmetric, binary symmetric Theoretic matrix with main diagonal 0. And I'm going to write it without bracket. And you have to really check that the parallel main diagonal, parallel entries are all the same. And it is also symmetric. So now this one is.
In order to avoid from the loop.
Sorry?
In order to avoid from the loop, we use
You only need those n-1 entries.
No. We write main diagonal to be 0 to avoid loop.
Yeah, that's right. Because the loop is rejected by our study of metric spaces. I explained already.
Yes.
So we are not we are not deciding not to have loops. We are deciding because of that reason. In mathematics, you have to really say that. Otherwise, your examiners will say, why did you arbitrarily choose this condition? And you have to answer that. Even if that condition is so silly and ground level, you need to give two to three good reasons. As soon as you give one good reason, the external is happy already. So, anyway, let us continue. 1, 0, 1, 1, 0. You need to check this is turbulent and symmetric binary. Column 3, 4, 1, 0.
It should be 0, 1. Yes.
And we have force 1, 0, 1, 0, 1, 0, 1, 0. This kind of thing I can't remember.
0, 1, 0.
0, 1, 0. And then we have these two positions of zeros. And that one gives us 1,
1, 1, 0, 1,
1,
0,
0,
1,
1. And here we have
0,
0,
1,
1,
1, 0,
0,
1,
1,
0.
So I'm omitting the bracket. We will now draw the corresponding undirected Turkish graph. This was I actually started with a real integer Turkish matrix.
Yes.
And then obtained two of these binary matrices. And this is one of them. Accidentally, it was symmetric. And then you can, now the vertices of the graph is labeled from 1 to 7 instead of 0 to 6. But it doesn't matter actually. So let us have 1, 7. And here we have, this way we come down 2, 3, 4, 5, 6. Let us write it.
Yeah.
And after obtaining the graph, we'll erase the labels. So what are we going to do? Vertex 1 is adjacent to 2, 4, 5.
Yes. 1 to
2,
1 to 4,
4,
1 to 5.
5. And that one is 2 is adjacent to 1, which we only look from the diagonal one.
Yeah.
So to reach 3 5, 6.
2, 3,
3,
2, 5.
5, 6. And then this one, third one is 4, 6, 7.
It starts from 2 to 3 and 2 to 6.
Sorry?
From the second row. 2.
I'm making mistake.
Yeah.
So the 2 was correct. The 2 was not.
Yeah.
That was not. These 2 were correct. These 3 wet edges are correct.
Yes.
2 is 2, 3.
2, 5.
2 is 2, 3,
2, 5, 6.
5, 6.
Starting from 2.
Yes.
Yeah.
2 is 2, 3, 5, 6.
Yeah.
3 is 2,
3, 2 already.
4, 6, 7.
Yeah. 3, 4.
4, 6, 7.
Yeah.
4 is 2,
4 to 1 already.
5, 7. 4 is to 5 and 7, right?
Yes.
5 is to 6 only
6.
now. And 6 is, you can only be
7.
6 is
6 to 7 in the previous row.
this one.
Yeah.
6 is to 7 and 7 does not matter anymore.
Yeah.
So this was the this graph
Yes.
which I have obtained from this binary symmetric Turkish matrix. Matrix is main diagonal 0.
Why we call it binary?
Correct?
0, 1.
Okay, okay.
All 0. And we get this Turkish graph. Here's Turkish graph now.
This matrix is adjacency matrix of this graph, right?
This is the matrix.
Yeah.
So we can define a triplets graph as a graph whose adjacency matrix is triplets matrix.
Yeah, binary Turkish matrix of symmetric, binary symmetric Turkish matrix of main diagonal also. Then we get undirected graph, finite. Now, we have already observed that this whole matrix is, because of the symmetry and the main diagonal, whole matrix is determined by these entries.
Yes.
How many of them? N minus 1. N is equal to 7.
Yes.
N minus 1. Now, their position, their column number in that first row are natural numbers. In this case, this is column 2.
Yes.
4, 5. So those 2, 4, 5 will determine this graph, right? That is how Professor Sheng Bau has converted this whole thing into this now. We're going to define Turkish graphs now without using any matrix. So that is how Professor Tampirescu and his students come down to this definition now, which is data structure-wise very economic. So let us copy this definition of a Turkish matrix without even knowing any Turkish or Turkish graph, without even starting from any Turkish matrix. This is the beauty of this type of mathematics. We don't need to really worry about Turkish operators or Turkish matrices. We worry about this thing here now, which is not we were going to define it. Let R be a natural number. And A be a set consisting of natural numbers. R of them. We can easily say that it's a subset of that. R subset of that. With a condition have to also observe that every next one of these positions is strictly greater than the preceding one. So we have A1.
Yeah.
This is actually at least 2 also. We don't even write it.
There should be A2, A1 strictly less than A2.
Thank you. And this one is strictly less than or equal to n. Is that right? So this is just a set of numbers we took, satisfying this condition. Then we can define a turbulence graph without having any turbulence matrix. The turbulence graph T is our NA. This N is the order, A is more or less a generating set order. It is not what A is the dose A. This is given by, so compact now because it is Ij, edges are just Ij. I going from 1 to n, j going from 1 to n, and I are not there. This so that distance between I and j is in A. Look at this very simple definition. Distance is in that set. Oh, wait a minute. This is the edge set, of course. Let me rewrite. Is defined by the specification. I'm using this many times now. With A, B equal to 1, 2 to n. E equal to 1, 2 root of n. So you are simply checking a non-negative number, actually it's a positive number, to be in a given set or not. If your program is, for example, using Python, you are simply checking the set of non-negative number, positive number. This is actually positive because I, j are never equal. This positive integer, whether it is in this set or not. And then you actually get the graph quickly constructed. There is a proposition which I will not write, I will just tell you, it's in the slides. The proposition is that you can see it from the way we obtain that graph from this. If you add this edge, in this case, if you add just this edge, every vertex will become degree 4. And this is a circular graph because now you can see that you can take that to be 0.
Yeah.
0, 1, 2, 3, 2, 6, set sub 6 again, and then you are taking 4, generating set of 4 elements. You can get this graph. That means that this gives you a hint that every turbulence graph is a spanning subgraph of circular graph. That was the proposition. Every turbulence graph, for every turbulence graph T, there exists a circular graph G, so that T is a spanning subgraph of G.
Yeah.
Spanning means a vertex set cycle, the subgraph and vertex set cycle. Can you manage to write it down? Then if T is any turbulence graph, it will be, then there exists a circular graph G, such that T is a spanning subgraph of G. My key question here. This original graph was turbulence graph. Is this turbulence graph Kelly graph? Quick answer.
Is two-plet graph
Is this graph a Cayley graph? Quick answer. Just yes or no.
I don't think because it is not.
No, because
Yeah.
there's degree C and this degree 4. We
Yeah,
said that
it's
it's
not regular.
Cayley graphs are regular of degree R.
Yes.
So this is not a Cayley graph. Okay.
Yes.
Now let us keep some. Now we're going to generalize. Okay. This is the last concept today, and we're going to bubble a little bit after that. This was one of my paper, which of course I was not the first one to do this, but two statements which are contradictory to each other are both true in such a reality. I was the first one to do it, and also I was not the first one to do it. The other, Zelinka was a Czech mathematician. He had wrote a long time ago, he has a paper of the same name. My paper was also the same name, but it is published, the journal didn't mind, because my concept actually covers more than his, so the more general. I didn't say I'm generalizing him, I was only saying that I'm generalizing these two classes. So he was able to do that. Another thing is that there, in this definition which I'm into right now, we don't require the vertex set to be finite. His graphs are all finite. So in that case it was fine because it is not plagiarism because I didn't copy from him. First thing is. Second thing is my paper has actually some merits in addition to that, his paper. It was Zelinka, we should really say Zelinka was the first one to do it. It is in my slides. The names are all in my slides, and my paper is also there. So let us now generalize. We are going to define a graph, directed graph, using a semigroup only. We remember that semigroup is a non-empty set with associated binary operations.
Yes.
It doesn't even need to have identity element. You need to have at least three very different, essentially different and essential examples of semigroups to your fingertips. Everybody, when people ask, here's one, here's two, here's three, you need to also have three essentially different, essential non-semigroup examples, which is easier to give. So now let us start with the semigroup. So this is called semigroup graph. This is where geometry questions are going to be asked about. Of course, it can be asked for Cayley graph and Turpin's graph, and I think Professor Sheng Bau is interested in the traditional Turpin's graph part. So we're going to define something called the semigroup graph. So this is my definition. Let S be a semigroup. What is it has that it has a binary operation which is associated. Nothing else. Nothing else we assume. Semigroup. This means that you know that the semigroup monographs, there are many of them. Howey is one of them. They look almost like set theory because very dirty this subject is. Because there's no much structure in it. But of course it's fairly new. And we assume that A is a subset of B is a subset of the semigroup. Then a graph can be defined. We're going to now X. This is set a semigroup graph. Semigroup graph XVS is defined with the specification below. So I'm omitting that word. So that Vx is V. That subset we chose from the semigroup. Is a set of natural numbers a semigroup?
Yeah.
Yes.
Yes.
And under addition and under multiplication, it is a semigroup because its multiplication and addition is
Yes.
closed and it is associated.
Yeah.
Only that we don't have any element
Yes.
except maybe one invertible under multiplication and no element to be invertible under addition.
Yes.
Yeah.
So
Delete one and then it will be semi-group under multiplication?
Also yes. So natural numbers is a very good example. You need to keep it at in your pocket
Yes.
for for interviews. Let me tell you.
Yes.
This interview is such a horrible thing now, especially when you fight for the same position. Wow, people are killed. You need to be very good at interview. No, this is not enough. You need to have very good papers, even if the number is small. You need to have good papers, beautiful papers. And then you pass your interview nicely. And then if people who are hiring, they also value good small number of papers, then you might be shortlisted before those who have lots of papers and failed the interview. There are people who have 150 papers and still can fail the interview. So this is very strange world now, because when I was looking for jobs, there was no competitor. I was lucky then. Now there are too many PhDs. This is why we don't really want to have too many PhDs in the same topic. Ex is given by the following. It's actually, you should carefully examine this H set. This H set is given by ordered pair. This requires that A is from the set A. So we're using A as a left multiplication to get to the vertex adjacent to B, adjacent from B. And then we need to also require that both B and AB are in B. This condition, referee can question you. And if you have a good reason to include this, you will be instantly convinced. Otherwise, this looks arbitrary or artificial. Nowadays, we can't say artificial because artificial is better than natural now, I think, something like that. Artificial intelligence is better than natural intelligence from what my impression these few weeks. Because everybody first checks the online thing, ChatGPT, and then try to read it. You should really try attempting to, for example, why we read this. You need to consider it first, and if you check online, you can't find it except by paper. So it is not good. Don't always prioritize artificial intelligence. So this has a good reason. When we see examples, you will probably start seeing the reason. Now, the main thing is, every Cayley graph is a semi-group graph. Number one, example. Only that now the semi-group is a group, and we have an three additional conditions on A. Every triplet graph is a semi-group graph, or where the semi-group is taken to be natural numbers because of that. Look. Two. Triplet graph. Is a semi-group graph. S is equal to n. And B is 1, 2, 3, 4 to n. B is n sub n. And A is there. So every triplet graph is a semi-group graph for this specific semi-group question. If these are the only, if every semi-group graph is either Cayley graph or a triplet graph, then we don't have a reason to generalize, do we? If every semi-group graph is either a Cayley graph or a triplet graph, then this definition I should reject if I'm referring it. This definition I should reject. So he didn't reject because I gave a third example. There are infinitely many graphs which are neither this nor that are semi-group graphs. and you can actually, let me show you one example. Just one example is probably enough. So that one example I can easily give, so I'll just hold on to it. There are, exist infinitely many, infinite family, semi-group graphs, even just from that. That are neither hairy nor tails. By giving this example, the referee doesn't have any query about rejecting this definition. Every finite vector group graph is a semi-group graph which is neither. I can give you just one example. So what is a vector semigroup? Vector semigroup considers the Euclidean plane. We are back in this all the time. And then you have this so-called Cartesian product which gives you coordinates and so on, but it doesn't matter. Here is the origin. Let us take any wedge like that. If all your vectors are inside here, UV, their sum is also inside, right? Their vector sum is also inside. If any vector is here, any scalar multiple is also in this wedge. So, set of vectors whose arrowhead is in this wedge is a module, or it is closed under vector addition and positive scalar multiplication. Positive scalar multiplication in this case. So if it is going that way, it is probably negative, still positive scalar multiplication. Such a thing is called this set. This set is called, is an example of a vector semigroup. Actually, it's a vector abelian group. Not only is it probably a module, because there's also positive scalar multiplication. So it's not a module, but it's abelian. And we're going to consider one of these. Not only consider one of these, even if your arrowhead is all on Gaussian integer points, then the still same thing holds if you take your scalar from the ring of integers, from the natural numbers. Then any two integral vector sum is also infinite, isn't it? Yes. Are we sure about it? Yes. And the positive integer scalar multiplication also is inside here. So we're going to take one such thing. So this can be written down in a general way. Where is my?
Professor, you said about Euclid plane. Then what will be the vertex set? What will be the edge set?
Vertex set will be all the vectors. Now this is uncountable already.
That means a graph can be on uncountable vertices also.
Yes, when we define graph, we didn't say V is finite set or even countable. We said it's any non-empty set and E is probably empty or probably any set. So let us write this down in a formal way. So let us just give an example. So the example outside 2 and 3, the 1 and 2. The general expression of this is in my slide, so it doesn't matter. Example of 3 and not 1 and 2. So let us take V equal to xy Now this is a Euclidean plane, so it's ordered pair of numbers. In this case, integers, natural numbers. X, Y are natural numbers, positive integers. And X is not greater than Y. Both of them are at least 1. And nothing exceeds 7. And Y is not greater than 3x. So here, there's one straight line is y equal to 3x. Another straight line is y equal to x. X, y both come from natural numbers. Y equal to x is given here. Y equal to 3x is given there. And we're taking all the natural numbers. Now we can draw it. I will erase this because when I try to fit inside, it will not be accurate. Anyway, it's between y equal to 3x and y equal to x. So what are they? Let me be careful. This is 1, 0, this point, this vertex. You try to figure out the coordinates. The coordinate doesn't matter to me. And these edges are there. This is the vertex. This is a vertex set. So, and we give A to be 2 unit vectors, individual unit vectors. Two integral non